Hi. In this video, we're going to continue our discussion of the number theory. Uh, in the previous theory session, we had talked about Fermat's theorem. Basically, the theorem stated that a power p minus 1 is congruent to 1 mod p as long as GCD of a and p was equal to 1, right? So now we are going to try to generalize this. The way we think about it is what happens when the modulo is not with respect to a prime number. So what if we take what if we take mod m, right? So if you recall the proof that we had discussed for this, the proof will break down if we do mod m, because what we did was we took all the numbers from 1 2 till p minus 1, in this case m minus 1. And if we try to say that that is congruent to a till m minus 1a mod m, basically we cannot cancel now. We cannot cancel 1, 1, 2 till m minus 1 because they are not necessarily relatively prime to m. They are not relatively prime to m. In the case of prime numbers, 1, 2, 3 till p minus 1 was relatively prime to p. Therefore, we were able to cancel the factors and we got the simple result that p minus 1, a power p minus 1 is congruent to 1 mod p, right? So how do we generalize this? So what we can do is we can get around this problem. We can get around this problem of not being able to cancel the factors by only listing out the integers less than m which are relatively prime to m, which are relatively prime to m. And that introduces for us the function called Euler's totient function, which is written as phi of m. So basically it counts how many integers less than m are relatively prime to m, right? So what do we do now? We say we are creating a new list of integers. Let's call it 1, R1, R2, and so on, which are relatively prime to m. Relatively prime to m. Therefore, if these integers are relatively prime to m and a and m have GCD equal to 1, then a times 1 and a times r1 and a times r2 and so on will also be relatively prime to m. Because this list of integers was those integers which were prime to m. Therefore, this list which we multiply with a, but a was relatively prime to m, so this is also relatively prime to m, and this list must be a simple rearrangement of this list, right? So basically, now we can say that a times r1a times r2a and so on should be equal to 1 into r1 into r2 and so on, this list mod m, because this must be a rearrangement of these relatively prime integers. So therefore we can do this. The number of such elements here, the number of integers here is basically phi of m, right? And now we can cancel out the numbers 1, r1, r2 and so on from both sides, because we know that these are relatively prime to m. Relatively prime to m. So once we cancel it out, what we get is all of these get cancelled. And what we get is just a, how many times? Phi m such type numbers. So we get a power phi m is congruent to 1 mod m, right? So this is true for all a and m that are relatively prime. A and M are relatively prime to each other, and that is known as Euler's theorem. Euler's theorem. Basically, it's a generalization of Fermat's theorem. So Fermat's theorem comes as a special case of Euler's theorem. So basically, if you put M is equal to P, you will realize that phi of P is simply P minus 1. So it will become A power P minus 1 is congruent to 1 mod P. Right? So that's how Fermat's comes from Euler's theorem. Okay. Now, what we want to think about here is, since A power phi of M is congruent to 1 mod M for AM GCD being equal to 1, every number relatively prime to M, relatively prime to M. So for example, every number like A, which is relatively prime to M, has a period mod M, and that period must be a divisor of phi of M, a divisor of phi of M, right? So we had seen earlier that the periods were like this: A power T is 1 mod M, and similarly A power 2T was 1 mod M, right? T was the period, right? So here we are getting phi of M. So phi of M must be a multiple of T, right? Or you can say, if T is the period, then phi of M must divide T. Basically, that's what I'm saying, right? Now, what we can say also from here is that any number not relatively prime to M, doesn't have a period mod M, doesn't have a period modulo M. Correct. So these are two basic things that you need to know. Now, what we will do is we'll analyze this totient function a little bit and find out some properties of this function. So first thing is, how do we find phi of p power k, where p is a prime, and k is a positive integer. So the meaning of phi of p power k is what? It means all the numbers less than p power k which are relatively prime to p power k, right? So which ones will it be? So let's think about it. Uh, so it since p is a prime, every number less than p power k except the multiples of p must be relatively prime to p power k, right? So basically, you you can start listing out the numbers from 1, 2, 3 till p. There are how many numbers in this range which are relatively prime to p power k? There are basically p minus 1 numbers here, because you have to exclude p. P is having a common factor with p power k. Similarly, from p plus 1, p plus 2 till 2p, how many numbers are there which are relatively prime? This will be these numbers. These are also p minus 1, right? So like this, you can continue and you can say, from p power k minus 1 plus 1 to p power k minus 1 plus 2 till p power k minus 1 into p, which is p power k, you get another p minus 1 numbers, right? So you are having k rows of numbers, right? And not k, we are having actually p power k minus 1 sets of such numbers, right? So from 1, then you went to p power 1 plus 1, then you went to p power 2 plus 1, and finally you went to p power k minus 1 plus 1, right? So how many rows are there? There will be basically p power k minus 1 rows of p minus 1 numbers. In each row, there are p minus 1 numbers which are relatively prime to p power k, and there are this many rows, p power k minus 1 rows. So therefore, the total number of numbers will be p power k minus 1 times p minus 1, which will be basically p power k minus p power k minus 1, and that is equal to value of phi of p power k. So this is giving us the number of numbers which are relatively prime to p power k, right? The next important property is the property that phi function is multiplicative. So phi of mn is equal to phi of m times phi of n, as long as m and n are co-prime to each other. M and n is equal to 1. The GCD of m and n is equal to 1. So what we will see now is a nice proof of this multiplicative nature of the phi function. Okay. So I will do it on the next screen. So let's list all the integers from 1 to mn in a grid, and we'll write the grid like this: 1, 2, 3 till m. Then here it will be m plus 1, m plus 2, m plus 3 till 2m, and similarly 2m plus 1, 2m plus 2, this will be 3m, and finally last element here will be n minus 1m plus 1, n minus 1m plus 2, and you go down till n minus 1m plus nm, right? So that will become equal to mn, right? So this is my rectangular grid of numbers from 1 to mn, right? Now consider, our job is to find phi of mn, right? Phi of mn is the total number of numbers which are relatively prime to mn, right? From this grid. Now consider any element r, which is not relatively prime to m. So basically the GCD of r and m is not equal to 1, right? So GCD of m and r is equal to d, and d is not equal to 1, right? Now if that element is in some row, think about it, it is here, let's say, right? This row. Any element in this row will be m plus r, right? Then 2m plus r, and so on, n minus m, 1m plus r, right? This is the row where we started off with r, which was not relatively prime to m, right? So all elements in this row, are not relatively prime to m, right? Because the GCD of m and r is d, so you can see that d divides definitely both of these, right? D divides both of these. So it divides m and divides r. It divides 2m and r. It divides n minus 1m and r, right? So there is a common factor. So D divides all of the elements of this row. So therefore, D will divide mn also. Notice that D divides m, right? because D is the GCD of M and R, so obviously D divides Mn also, right? So therefore, the GCD of any number here, Mn, with any number here, 2m plus R, is not going to be 1, right? It has to be at least D. Please take a moment and try to think through it. We are taking an element R, which is not relatively prime to M. Every element of this row will be like this, R, M plus R, 2m plus R, right? And if the GCD of M and R is D, then D divides all of the elements in this row, right? If D divides M, then obviously D divides Mn, and therefore Mn also has a common factor D, and any element of this row also has a common factor D. So basically we can exclude this row from our thinking, right? Because all the elements in this row are not relatively prime to Mn, right? So when we start to count elements which are relatively prime to Mn, we only need to consider rows. We only need to consider the rows starting with elements, starting with the elements which are relatively prime to M, which are relatively prime to M. Because anytime you get a row starting with an element which is having a common factor with M, then that row has no number which is relatively prime to Mn, right? So how many such numbers are there which are relatively prime to M? Obviously that is phi of M. By definition of the totient function, the number of such a numbers is phi of M. So out of the M rows, I only have to think about how many rows? I have to think about phi of M rows, right? Where the starting number of the row is relatively prime to M, right? So we have figured out how to count, which rows to count and which rows to exclude, right? We have 5m rows which we can count, okay? Now we'll focus our attention on elements inside a particular row, right? Let's go to the correct sort of a row which starts with an element which is relatively prime to M. And in those rows, we are going to count how many are further in those rows, which ones are overall relatively prime to Mn, right? So what we will say is, now consider one such row made up of elements k times m plus r, where k goes from 0 to n minus 1, and obviously m and r have common GCD is 1. So m and r are relatively prime to each other, right? This row has how many elements? This row has, if you see, every row here has n elements, 0 to n minus 1, right? Has n elements, and no two of the elements are congruent to each other mod m, are congruent mod m, mod n. Why? Because it has n elements. If two elements were congruent to each other mod n, then we can say that km plus r is congruent to jm plus r mod n, and then we can subtract r and we can say km is congruent to jm mod n, and we can divide by m because n and m, in the beginning only we have said n and m are co-prime to each other, right? So then we are getting k is congruent to j mod n, right? But k is congruent to j mod n is a contradiction because these are two different rows. K and j are different numbers. So these are two different rows. So basically now we can say that since we have n elements in each row and no two of them are congruent, right? Yeah, I'll just write it here. So what I'm saying is there are n elements in each row. No two of them are congruent modulo n. So the elements, therefore, the elements of the row must be a rearrangement of 0, 1, 2 till n minus 1 mod n, right? These are the all possible residues mod n, and we have n elements. So each of them must correspond to one of these congruence classes, right? They are all in different congruence classes. So obviously, how many of these numbers will be relatively prime to n? The number of such numbers will be phi of n. Phi of n numbers in each row will be relatively prime to n, right? So from this, what we are concluding is that there were phi m rows to consider, and in each row there were phi n numbers relatively prime to n, and therefore the total number of numbers that are relatively prime to m and n should be the product of these two, right? In each row you'll count this many, right? So total number of numbers will become phi m times phi n. Therefore we are establishing our main identity, the multiplicative nature of this function, which is giving us this result if m and n are co-prime to each other, right? Now this helps us figure out the values of phi of any number, because we can say phi of m is equal to phi of, let's say, m's factorization was p1 e power 1, p2 e power 2, and so on till pk e power k. Since each of the prime numbers are co-prime with each other, we can use the multiplicative nature to write it like this. And then we can use the previous results that we proved. So phi of p1 power e power 1 would be simply p1 power e power 1 minus p1 power e power 1 minus 1. And this will be p2 power e2 minus p2 power e2 minus 1, and so on till pk power ek minus pk power ek minus 1. So we can take p1 power e1 common, and you get 1 minus 1 by p1. P2 power e2 common, 1 minus 1 by p2. And similarly, pk power ek common, 1 minus 1 by pk. And then the product of p1 power e1, p2 power e2, pk power ek was simply m. So this becomes m times 1 minus 1 by p1, 1 minus 1 by p2, 1 minus 1 by pk. This is the result. It's a nice looking result. So phi of m is equal to m times 1 minus 1 by p1. These are the prime factors of m, right? So that concludes our basic discussion of the nature of the Euler's Totient function. Now we come to the next idea in the theory, which is Wilson's theorem. So it is not applicable at many places, but when it is applicable, it is quite powerful. It says that for any prime p, we have p minus 1 factorial is congruent to minus 1 mod p. So p minus 1 factorial modulo p will be minus 1, right? So this theorem works only for primes. If you think of a composite number, if m is composite, let's say, right? And you try to figure out what is m minus 1 factorial mod m, then you will realize that if m was equal to, say, a times b, m minus 1 factorial will be m minus 1, m minus 2, and so on till 1, and a and b will appear in this product, and therefore you can show that m minus 1 factorial is congruent to 0 mod m if m is composite. So this is a result that you should know. For the prime number case, what we can see is we'll do the proof for the prime number case. So we have to show that p minus 1 factorial is congruent to negative 1 mod p. Okay. Now what we can do here is we consider some primitive root g, consider some primitive root g modulo p, and by the definition of a primitive root, we know that the period of this g, period of g mod p is equal to p minus 1, right? So all the numbers g, g square, g cube, right, till g power p minus 1 are basically, one second, hold on. Correct. Yeah, I'm right. So the period of g, because of it's a primitive root, is p minus 1. So g power p minus 1 is congruent to basically 1 mod p, right? Now, so these set of products are basically, all of them will be congruent to 1, 2, 3, some rearrangement of these p minus 1 mod p, because there are p numbers here, and the first time it starts repeating is when it hits 1 here. So everything else is going to be in distinct congruent classes. These are all incongruent with each other, right? So it must be a rearrangement of this, right? Correct. So when we try to calculate p minus 1 factorial, that is equal to 1 into 2 into 3 into p minus 2 into p minus 1. And since all of these are rearrangements of this primitives, so we can replace them and say it is g into g squared till g power p minus 1, which comes out to be g power, you add the powers 1 to p minus 1, it becomes p into p minus 1 by 2 mod p, right? But now you have to realize that g power p is same as g. So basically this becomes g power p whole power p minus 1 by 2. So that is equal to g power p minus 1 by 2, right? So what we have gotten so far is p minus 1 factorial is congruent to g power p minus 1 by 2 mod p, right? Let's take, let's take the substitution t is equal to g power p minus 1 by 2, right? So then t square is congruent to g power p minus 1, which is equal to 1 mod p. So we know that t square is congruent to 1 mod p, therefore t square minus 1 is congruent to 0 mod p. So t minus 1 into t plus 1 is congruent to 0 mod p. So t can either be plus or minus 1 mod p. And we'll show that t will never be plus 1 mod p. Why? Because if t was equal to t, which was equal to g power p minus 1 by 2, if that was equal to 1 mod p, that is a contradiction, because we know that the period of g by definition is p minus 1, but here we are getting p minus 1 by 2, which is less than p minus 1, is giving power g power p minus 1 by 2 is coming as 1 mod p. That cannot happen. The first time g powers will become 1 is when it is g power p minus 1, right? So t can definitely not be equal to 1 mod p. So t must be congruent to minus 1 mod p, which means g power p minus 1 by 2 is congruent to minus 1 mod p. And what was g power p minus 1 by 2? That was p minus 1 factorial. We get p minus 1 factorial is congruent to minus 1 mod p, right? So that is our proof of Wilson's theorem. So that concludes the basic information on number theory that you need for most of the problems. We'll continue our discussion in the next few videos. We'll see some practice problems on all of these ideas, and then we'll even go to quadratic reciprocity. So we'll do some advanced theory here. So stay tuned, keep watching the videos, and let me know if you want to know something else. Please like and subscribe the videos. Like the videos and subscribe to the channel. That helps me grow the channel. So I'll see you next time.